for us to take a look at the binomial probability distributions. If you're familiar with the word binomial or bi, the prefix bi in English means two. So when we're talking about a binomial experiment, we're talking about an experiment or an event that has only two outcomes, or it can be reduced to two outcomes. Excuse me. So for example, if we toss a coin, the options are heads or tails. So we have two outcomes. When a baby is born, it is a boy or a girl. Again, two outcomes. In any kind of sporting event, you can have a win or a loss, two outcomes. On a quiz, especially if it's a true-false, you have two outcomes, true, false. We can reduce things like medical treatment and look at whether it is effective or ineffective, whether blood pressure is normal or abnormal. Even rolling a die, we can think about it as we roll a 5 or roll the number that we want. And then the other category is that we do not get the number that we want. So like 5 would be what we want, and not 5 would be what we don't want. Multiple choice, we can reduce that to two outcomes and have your correct answer and your incorrect answer. So when you're thinking about a binomial experiment, there are actually 4 requirements for an event to be a binomial experiment. First of all, there has to be a fixed number of trials, which is typically represented by the lowercase n. You can think about it like the sample size. How many times are you going to flip the coin? How many true-false questions are you going to have on a test? How many sports games are you going to look at? So you have to have a fixed number of trials, and that should be typically stated in the question or in the problem. Each of your trials can only have two outcomes, or can be reduced to two outcomes. And we typically refer to those two outcomes as a success, meaning you get what you want, and it's typically represented by a lowercase p. Or you have a failure, which means you do not get what you want, and that's usually represented by q. And the relationship between p and q, you can look at it one of two ways. If we add based on our probability information that we have, we take the probability of failure plus the probability of success, probability of success plus the probability of failure. That has to equal 1. So p plus q has to total 1, because something is going to happen when we flip the coin or look at a sporting event or answer a true-false question. The outcomes of each trial, the third requirement is that the outcomes of each trial must be independent of each other. That's basically a fancy way to say the outcome of the first trial or the response you give to the first question does not affect the second question, which does not affect the third question, and so forth. So it's kind of like they're, standalone individual events. And finally, the probability of success, and remember, probability of success is represented by the lowercase p, must remain the same for each trial. It doesn't change from trial to trial, meaning you're flipping the same coin every time, or you're using the same deck of cards, and that kind of thing. So you're not changing the probability of success from trial to trial. So we can, it's not convenient, it's a yucky formula, but we can calculate the corresponding probabilities for each outcome of a binomial experiment using a formula. We can also, there are tables that will help us do it, or technology. I'm going to do one example by the formula so that you can see that it does work, but primarily we're going to use technology. Specifically, we're going to let Minitab calculate the probabilities for us because it's more important that we understand how to interpret that probability or that value than it is that we can manually calculate it. The other thing that's challenging about the formula is it only lets me figure if I have an exact number of successes. But if I want to figure out, what if I want fewer than X successes or more than X successes, then I've got a lot of calculations that I would have to do by hand. So again, we will ultimately focus on the technology, but I am going to do the first example here by hand just so you can see that it can be done. But then also, hopefully, you'll appreciate the technology. So taking a look, our scenario here says we're going to flip a coin 5 times, and then we want to find the probability of flipping exactly 3 heads. Well, before I begin this problem, I may want to confirm that this is a binomial. And to confirm that this is a binomial, I have to see if I meet the four requirements. So the first requirement is that we have a fixed number of trials. And if you look at this first sentence, it says flip a coin 5 times. So I'm told in the problem that my number of trials is 5 because I'm going to flip the coin 5 times. The second requirement is that I have 2 outcomes. Well, again, hopefully you realize that when you flip a coin, your options are you're either going to flip a head or you're going to flip a tail. So I do have 2 outcomes. Third is that your trials are independent. And what I'm going to think about there is, does it matter whether I get a head or tail on the first flip? Is that going to affect whether I get a head or tail on the second flip? It doesn't. So the trials are independent, so I do meet that requirement. And the last one is that the probability of success, which is P, is basically constant. So if I'm flipping a coin and I'm flipping the same coin 5 times, then that is going to be constant. If we think about what that would be, our success here is we want to flip a head. So the probability of getting a head when I flip a coin, I hope you realize, would be 1 out of 2 or 50%, 0.5. So flipping a head is 0.5, which is my probability of success. So that would be my P. If I think about my failure, which would be that I flip a tail, well, flipping a tail is also 1 out of 2. Remembering that it has to total to 1. So in this case, Q, which is my probability of failure, is also 50%. So then I'm going to plug into that lovely formula that was on the last screen, and I'm going to write it down here on this screen, and then we'll talk about it. We take n factorial divided by n minus x factorial times x factorial times the probability of success raised to the x power times the probability of failure raised to the n minus x power. Again, that's a doozy of a formula. And if you're not familiar with a factorial, what a factorial does is you start at n and you count your way down. So you would do n times n minus 1 times n minus 2 all the way down to 3, 2, 1, and you multiply those values together. So you would start at the value for n and count your way down to 1. So I'm going to plug and chug what I know into this problem. Okay, so n is the number of trials, which is 5. So I would have 5 factorial divided by 5 minus x. X is the number of heads that you want, which in this case is 3. So I have 5 minus 3 factorial times 3 factorial. We decided the probability of success was 0.5 raised to the third power. Probability of failure is also 0.5 to the 5 minus 3 power. So I'm going to do a little bit of simplification first. So I have 5 factorial divided by 5 minus 3 is 2 factorial, 3 factorial times 0.5 to the third power times 0.5 to the second power. Now, if you have a TI 8384 calculator, possibly even just a basic handheld calculator, you may be able to do your factorials on your calculator. I'm going to try to do some simplification here just by hand. So it would be 5 times 4 times 3 times 2 times 1. That's 5 factorial. Then in the denominator, I have 2 times 1. That's 2 factorial. Times 3 times 2 times 1. That's 3 factorial. And if you'll notice, in that particular problem, I have a 3 in the numerator, a 3 in the denominator, 2 in the numerator, 2 in the denominator, 1 in the numerator, 1 in the denominator. So those values will divide out. I also can divide 2 into 4, which is a value of 2. 2 goes into 4 2 times. So, and then I just have a 1 in the denominator. So I have 5 times 2, which is 10 over 1, times 0.5 to the third times 0.5. 5 minus 3 is 2. So I basically have 10 times 0.5 to the third times 0.2, or excuse me, 0.5 squared. So I can use my calculator at that point. Again, you can do all of the calculations on your calculator, but I have 10 times 0.5 raised to, was it the third power? Do I remember right? To the third, raised to the third power, get out of the exponent, times 0.5 raised to the second power, get out of the exponent, hit enter. So I get 0.3125. So the probability that I would get exactly 3 heads when I flip a coin 5 times is approximately 31%. Now again, that's a lot of math involved, guys. And so, and we only can do if we want exactly 3 heads or exactly 2 heads or exactly 4 heads. So the formula is limited in its use. So instead, we will use Minitab. And remember, we're currently using the Minitab app, which is version 20. You can go to app.minitab.com. And what you're going to do is you're going to enter the possible values for x in the column 1. And then we choose the command. We go to Calc, scroll down to Probability Distributions, and then we choose Probability Density Function. You should at that point get a pop-up window where you have to enter about 6 pieces of information. You have to enter the form of an input. Are you doing a column of values or a single value? We typically do a column. Where did you put the values? We're typically going to put them in column 1. We have to choose the type distribution. There's lots of different distributions we can calculate within Minitab. At this point, our focus is on the binomial. Then we have the number of trials. How many times are you going to perform the experiment? What's the probability of that particular event? And then for output, I prefer just to go ahead and store the answers in a column next to the one that I already entered. Now that's your choice as far as a preference. The other thing I'll mention is that with this, it's going to calculate the individual probability values for each value of x. But that also opens up a world of possibilities where we can do an exact value, we can do a less than, a greater than or equal to, less than or equal to. Guys, you need to make this table with the instructions on how to interpret the binomial your BFF. I would strongly suggest that you put this table on the notes sheet that you're allowed to use for the midterm exam. Furthermore, I would tell you to print it off and have it handy as you're working on your practice problems and your homework problems related to the binomial distribution. So I want to try to walk you through some examples in Minitab. So if our example is a student takes a 10-question true-false exam and guesses on each question, find the probability of getting, and you can kind of read between the lines here, probability of getting exactly, it doesn't say it, but it kind of is implied, exactly 5 out of the 10. It's important to look for those keywords like exactly, less than, greater than, at most, at least, because that's going to tell me which of these procedures to follow on this table. So I'm going to use, in this case, the row for exactly. Okay, so the first thing that you do, and I'm going to do this in Minitab as we go along, is you go to Minitab, and in the first column, since I don't have any other data in there, I have to enter all of the possible values for x. So if I'm going to answer 10 questions on the true-false exam, and I want to know how many I got correct, so we're going to call this the number correct. It could be that you don't get any of them correct, and that's one where students forget. You have to start at 0. So I could get 0 correct, or I could get 1, 2, 3, 4, 5, 6, 7, 8, 9, or I could get all 10. So I put in the numbers, all of the possibilities. I can have 0 correct, 1, 2, 3, 4, 5, 6, 7, 8, up to 10 correct, because there's 10 questions, and we're told that in the problem. Then we go to calc, which is short for calculate, at the top of the screen. We're dealing with probability distributions. And under the probability distribution command, it gives you 3 different ways to calculate it. We calculate it using the probability density function. So it's calc, probability distributions, probability density function. And then we have to enter 6 things. You have to tell us the form of input. Are we going to input a single value, or are we going to say use a column? We typically are going to be using a column. So I change the form of input using the drop-down bar to a column of values. I have to tell Minitab where are those values. My values are in column 1. I can double click 1, 2, and it puts it into the box. At this point, the third thing you have to choose is the type of distribution. And again, we'll be talking about different kinds of distributions. This one is the binomial. We will also later talk about the normal distribution and also chi-square. So you have to choose which distribution you are using. We're using binomial. For the binomial, and to perform the calculations, the computer needs to know two things. It needs to know the number of trials, how many times are you performing the experiment, and then the event probability. So the number of trials here, where we're going to flip or answer 10 true false questions. So the number of trials is 10. The event probability, which is the probability that we get the answer correct. Okay, and I have two choices because it's true false. So 1 out of 2 would be 0.5 or 50%. As far as the display, you can have it create a whole nother table. For me, it's just as easy to tell it to store those values into the column of data that I already have selected. So I'm going to choose store probability density values in a column. I'm going to click OK. And Minitab automatically, using that crazy looking formula, calculates all of those binomial probability distributions. I can then use that to help me answer the questions. But again, I have to be really careful, make sure I read it correctly. Okay, so let me go back to the question. The question was, find the probability of getting exactly 5 out of the 10 correct. Okay, so since it says exactly, if I look at my table of instruction for exactly, the instructions say read the results directly from Minitab for X. So I would look for the number 5. Okay, so the number 5 are correct. 5 are correct. The probability of that is 0.2460094. Okay, so if we're doing exactly is a direct read from the printout. Okay, so it's a direct read. You don't have to do any kind of addition or change anything. You may need to round depending upon the instructions. So the answer here is 0.2460094. You can see all of the options that I put in to Minitab. Okay, but again, let me walk you through that. You enter 0 to 10 in column 1. We go to Stat, Probability Distributions, Probability Density Function. We want to do a column of values. My values are in column 1. I'm doing a binomial, and it has 10 trials with an event probability of 0.5. And I'm putting them in the column. All right, so let's look at another one. This one says it's the same question, but instead of being exactly 5, this one says, what's the probability of getting at least 5? Okay, probability of getting at least 5. And again, I'm going to go back to my table, and if I find the probability of at least 5, the instructions say add the results from Minitab for X, X plus 1, X plus 2, so forth, all the way up to N. Okay, so if I'm looking at my printout from Minitab here, that means I've got to add together the values for 5, 6, 7, 8, 9, and 10. Now, you can do that on your handheld calculator. You just have to be extra careful about typing them in. The other thing you can do, which might be a little bit easier, is if I come over here to Minitab and I highlight the ones I want. I want 5, 6, let me see, 5, 6, 7. Okay, it won't let me do it one at a time, but I want 5, 6, 7, 8, 9, and 10. Let's see. I can tell it to calculate the column statistics, and I want it to sum it. Okay, but it's going to do all of them. So I've got to try to move this stuff. So I might can copy it. Let's see. If I highlight them that way, let's see if I can copy them that way. That might work. Okay, sometimes we have to figure it out on the fly. Okay, so I highlight my numbers. I want to do 10, 9, 8, up to 5. So I want those values. So I'm just going to copy those, if it'll let me. Well, Minitab's being difficult, but you can, Miss Ralston can get it to work. Copy those over in the spreadsheet and let Minitab do it for you. Now for me, it might be just as easy then to do it by hand. So let me see if I can get my calculator. Okay, so we would take our calculators and we would do 0.246094. Notice I'm not rounding. Plus 2.205078 plus 0.117188 plus 0.043945 plus 0.009766 plus 0.000977. Okay, so we add those numbers up and we get 0.62348. So the probability that we would get at least 5 out of the 10 correct is about a 62% chance. Okay, you need to be extra careful about putting them into the calculator. Okay, take your time. All right, so this one says, according to a recent survey, 5% of Americans are afraid of being alone in a house at night. If a random sample of 20 Americans is selected, find the probability that, and it gives this list. Now I've recreated the table here, but I want to walk you through Minitab one more time. Okay, so I'm going to change and get a new project so we have a clean sheet. Okay, so in the first column, you're going to have to enter the possibilities for your variable. So we got to put in the number of Americans who are afraid of being alone at night. So I could put maybe number of Americans. And it tells us that we're going to consider 20 of them. So it could be we go from 0 to 20. So I enter those values beginning at 0 and counting to 20. Okay, careful. Make sure you enter the numbers correctly. You don't skip any. Okay, so I get numbered to 20. The 5% that's given here, this is the probability that they're afraid of being alone at the house at night. So that actually represents our P. This 5% is P. We write it as a decimal, so that's 5 divided by 100, which is 0.05. So in Minitab, I would go Calc, Probability Distributions, Probability Density Function. Again, we want to do a column of values. My values are in column 1. We are dealing with a binomial distribution. I have 20 trials, and my event probability is 5% written as a decimal. And I got a typo there. And I prefer to store them in a column. and I click OK. Whoops. Okay, column of values, number of Americans, binomial, number of trials. Okay, let me go through these again. I appear to have an error. We're doing a binomial, 20 trials. Okay. Illegal sequence of arguments. Okay, I got some kind of error here. I'm not sure what it is. Okay, but we entered our number of Americans. Okay, probability distributions. I asked it to display a table since it didn't seemingly want to put it into a column for me. So again, I get the table and it's up in the screen in the top half. I don't know why it wouldn't put it into the table for me. So if we go over here and we try to answer these questions using that output, okay, it says, what's the probability exactly 5 are afraid of being alone at night? Okay, when it's exactly, again, you can go back to that table, but exactly, we typically read it directly from the table. So I'm looking for 5. Make sure you're reading the column for X. So X is 5, and I get 0.014786. So for exactly, guys, when you're looking at this table, it is a direct read. Okay, let's look at most 3. And I'm going to go back up here to my table, and I see the keywords at most. So for at most, it tells me add the results from Minitab for 0, 1, 2 up to the value that you're given. So if I want at most 3, that means I want to look at the values for 0 plus 1 plus 2 plus 3. Okay, so I would take the answers that I got here from 0, 1, 2, 3, and I would add them together. And again, I can use my calculator to do that on my handheld calculator. I just need to be extra careful about typing the numbers in. Okay, so I have 0.000001 plus 0.000019 plus 0.000181 plus 0.001087. So I add those numbers up and we get a value of 0.001288. We added these together to get at most 3, following the directions from our table. The last question here is at least 7. So if I go back again and look at least, okay, at least says add the results from Minitab from X all the way up to N. So in this problem, that means we got to do from 7, we would start at 7 and go all the way down to 20. So we would add these values together to get the answer for the last one, and I'm going to let you do that one on your own. The last thing that I want to mention here is that we can find the mean and the standard deviation of a binomial distribution. The mean is the number of trials times the probability of success. The standard deviation is the square root of the number of trials times the probability of success times the probability of failure. Okay, so if we look at the same example we were just looking at, where we have n was 20, probability they were afraid of not is 5% or 0.05, which would then make Q 1 minus P, or 0.95%. If 5% are afraid, that means 95% are not. And so if I want to find the mean, that's simply the sample size times the probability of success. So we would have 20 times 0.05. And again, I'm just doing these calculations on my little handheld calculator. So I have 20 times 0.05, which is 1. So the mean would be 1. The standard deviation is the square root of n times p times q. So we would have the square root of 20, which is my sample size, times 0.05, probability of success, times 0.95, which is the probability of failure. So if I multiply those numbers together, I get 20 times 0.05 times 0.95 gives me 0.95, and then I'm going to take the square root, and the square root of 0.95 gives me a standard deviation of 0.9747 when you round it to 4 places. It's a pretty straightforward calculation as long as you're able to identify P and Q.